Okay. Good afternoon, everyone. Let's get started. Okay. So, sorry, maybe I should make the volume a little bit lower. Does that sound good? Okay, thank you. So, let us continue with the probability. So, a quick review. In the last lecture, we talked about the definition of probability and the conditional probability, right? And we know the probability essentially is a function, right? Which maps events to a number between 0 and 1. That number is usually abbreviated as probability, namely the chance of that event to happen, right? So the event, as we defined, it is just the sets, right? So that means once we have, oops. Hello? This might be better. Maybe I should put it. How about this? Okay. So that means like once we have the probability for sets, then we should be able to compute the probability over the operation on those sets, right? Here we're gonna review the 3 most important rules to compute probability after doing set operations, right? The first one is called inclusion-exclusion rule, right? So basically, suppose you got even A, you got even B, right? The probability of A union with B is computed by, you just sum up the probability of A and probability of B, but then subtracted by the probability of A intersection with B. Okay? We explain it in a intuitive way, like you can draw the Venn diagram, right? This is A and this is B, and the probability just calculate the area of those shapes, right? So probability of A union B is just the area of the shape after you merging A and B, right? And it is equal to, you look at area of A only, you look at the area of B solely, and of course, when you add them together, you kind of add the overlapping part for twice, right? That's why we need to subtract by the probability of intersection with B, that is subtracting the overlapping part. So that's the intuitive explanation. So when A is not overlapping with B, which means A intersection with B is empty, and this part is simply 0, right? Then the probability of A union B is simply the probability of A plus probability of B, right? Again, I hope everyone will just draw some figure to strengthen your understanding, right? And complement rule, if you got probability over even A, then the probability of A complement is just 1 subtracted by probability of A. And third one is called difference rule, right? If you know A's probability, B's probability, if you want to look at the probability of A minus B, so what is A minus B? What's the side difference? Anyone can recall the definition? Yeah. Exactly, right? Thanks. Right. So just excluding elements in A, which are also in B, right? It is A minus B, right? So if you want to compute the probability of A minus B, you just subtract the probability of A by the probability of A intersection with B, right? So we also have a very nice intuitive explanation on that, right? Suppose this is A. So probability of A minus B is just the area corresponding to A with the overlapping part deducted, right? So this is simply, you just look at the whole area of A and then subtract it by the overlapping part. So those are very important because we're going to repeatedly leverage those rules to get some results. Okay, so and then we define the so-called conditional probability, right? So the reason we introduce this concept is trying to build up the relationship between different events, right? So we define the probability of event A given event B happen as a ratio. This ratio is between the probability of A intersection with B and the probability of B. So this is definition. So don't ask me why, this is just the definition. It's a way to define what's the chance that A happens condition on that B has already happened, right? So, and be careful, conditional probability usually not equal to marginal probability, meaning that condition on some event B, you see it happens, right? This chance is different than it happens without condition on any event. It's really different, right? So this is the two concepts. Any questions? As I just want to like repeat experiment. No, example we discussed in the last lecture, right? So consider even A is like I get up late in the morning, right? B is like there's a big snow in the morning, right? So the chance that I get up late, right? This usually low, like say 0.1, right? Maybe I should put it 0.05, right? But then condition on that there's a big snow, then the chance I get up late might increase to 0.6, right? So this is the difference. There's a difference. Okay. And if we rewrite the definition of the conditional probability, right? If you multiply the denominator on both sides, we have another relationship here. That is the probability of A intersection with B is equal to the probability of B times the conditional probability of A given B happens, right? So the probability of A intersection with B, in many literature will say this is called a joint probability, right? So this means like A and B happens jointly, right? This probability equals to the probability that B happens times the probability A happens given B happens. Okay. Any question? This is a very, very useful relationship, which kind of like use it again and again to demonstrate other ideas and results, right? And symmetrically, we can also write it as the probability of B happens given A happens times the probability of A happens, right? Yeah, if you feel uncomfortable, we can think about what's the definition of conditional probability of B given A, right? From the definition, well, here is just you switch in B, right? So it will be the joint probability of A and B, which means probability of A intersection with B, divided by the marginal probability of A, right? Okay, that's the definition, right? And then you multiply this guy to the left, right? So you got another way to represent the joint probability, which is P of A times the conditional probability of B given A. Any question? Okay, so now with the those definition in our mind, right? We want to do some kind of practice, like some kind of example to strengthen our understanding of those concepts, right? So let's do some two problems, like in-class problems, right? The first problem is as follows. Suppose you throw a die, right? And it's a fire die. That means like you throw it, you got equal chance to say point 1, 2, 3 until 6. Okay? You throw this die for twice. Okay? And we consider two events. Event A be the event that the sum of the values is 5. Is 5. What? Sorry. Hello? Hello? I guess it's sorry, I guess it's running out of battery. Hello? 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 Sorry, just 1 minute. Hello? Hello? All the batteries are dead. Sorry. Oops. Hello? Oops. That's disaster. Okay. The last try. Why the projector is dead as well? Hello? Hello? Okay, here we go. I'm sorry. Um, yeah, I don't know. What's the problem with the projector? Um, Sounds like the projector is restarting. What? Um, Okay, perfect. Yeah, thanks for coming back. Okay, sorry. Yeah, let's continue, right? So we want to look at even A, which if you draw a fire die for twice, and the sum of the values is 5, right? That's even A. And I want to look at another event. Through the 2 points, I'm saying, at least one theorem is 2, right? So we want to calculate the conditional probability of A given B, right? So to see that, right, we're gonna leverage the definition, right? So according to the definition, how do we calculate conditional probability? Exactly, right? So we just, nothing strange, we just follow the definition, right? It is just the probability of A and B, or A intersection with B, divided by the probability of B, right? So then the remaining task is that we need to find out the probability of A intersection with B and probability of B, right? So to do this, we'd better to write down a corresponding set, right? How do we represent A? Sorry. Let us just enumerate, right? Yes, yes, right. So A talks about the sum of the values 5, right? So we can just enumerate. So if the first point is 1, then what's the value for the second point? 4, right? Because their sum is 5, right? So if the first point is 2, 3, right? I heard that. 3 will be the second point, right? If the first point is 3, 2, right? And if the first point is 4, second is what? 1, right? And what if the first point is 5? Why? Because it's not possible, right? If it is 5, then the next point must be 0. You won't see a 0 point. Remember, through a die, the only outcome you can say is just 1, 2, 3, 4, 5, 6, right? So there won't be some outcome like 5, 0, right? That won't happen. So you don't have this. Does it make sense? Right? So that actually is the set for event A, right? It includes all outcomes. I mean, by outcome, it means like after you roll the die for twice, right? Such that you see the sum of values is 5, right? There are no other possibilities, right? No other possible outcomes, right? So then what is B? B is an event that at least 1 through you see a point 2. Any proposal? We just okay. Yes. 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 Exactly, right? Yeah, we just follow what he said, right? So just enumerate all possible cases, right? So it says that at least 1 throw is 2. Let us consider, okay, what if the 2 we say is the first point? So you mean that means like the first point is 2. The second point can be arbitrary from 1 to 6, right? So you got 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Right? Okay. But there is another case where we see the point 2 in the second row, right? So that basically means you got 2 in the second draw, right? And then the first draw can be 1, right? And then the second draw is 2, and the first draw is also 2, but now you see it's repeated, right? You haven't seen that in our previous enumeration, so we just remove it. So then it will be the case that, sorry, your second draw is 2, but the first draw is 3, right? And second draw is 2, and first draw is 4. Okay. Second draw is 2, first draw is 5, and finally, second draw is 2, and first draw is 6. Okay, I believe I have enumerated all possible outcomes that match this, right? So at least one draw, you see the point 2, right? There won't be any other possible outcomes. Does it make sense? Okay. So then what is A intersection with B? You just look at these two sets and say which are in common, right? So what is A intersection with B? Yes, exactly, right? So if we just look at it, it will be here and here, right? Because in all the other element A, you don't see 2, right? So that won't be possible inside B, right? So A intersection with B will be just 2, 3, and 3, 2. Okay, then the next thing is I will just compute the probability. So to compute the probability, we need to know what's the sample space. Right? You draw the die for twice, right? What's the sample space? Sample space is the universal set that contains all possible outcomes. Right? What's the sample space? Any thought? Yes. You want to supplement or you have? Okay. Yeah. So you just well, it's kind of tedious, right? You just enumerate all possibilities in the first point and second point, right? You can imagine it's 1, 1, 1, 2, da da da, and 1, 6. Right? That's one possible case. And then in the second point, in the second row, you could be like have a 2 in the first trial and 1, 2, 2, 2, 6. You just enumerate, right? You just enumerate all possible combination of the points you could say for the first draw and the second draw, right? So it will be 6, 1, 2, 6, 6, right? In total, it will contain 36 outcomes, right? Everyone agrees with this, right? Any question? Okay, then use this where it is enough for us to compute the needed probability, right? So first, what is the, remember we need to compute 2 probabilities, right? In the denominator, we want to compute P of A intersection with B, right? So what's this probability? Yes. Remember, it's just equal likely, right? So that means like the probability is just the size of the event divided by the size of sample space, right? So which is 2. The size of A intersection with B is 2, right? Over the size of sample space, which is 36. So then what is the probability of B? Yeah, 11 over 36, right? Why is 11? Because the size of B is 11, right? So just if you just count 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, together 11, right? So it's 11, 36. And then through the definition, the conditional probability of A, conditional B is the probability of A intersection with B over the probability of B, right? Just the substitute numbers, which is 2 over 36, 11 over 36, which gives 2 over 11, right? Yeah, that's the way we compute that. Right? Any questions so far? Okay, great. I mean, this is a little bit tedious, but this is how we define and calculate that. Okay, another example to strengthen our understanding, right? We consider another experiment, right? So you got 2 urns, right? In urn 1, you got 4 black balls and 3 white balls, right? In urn 2, you got 2 black balls and 2 white balls. So now the experiment is carried out as follows. You randomly pick up an urn, meaning that you got equal chance to pick up urn 1 or urn 2, right? And then you randomly select a ball from that urn, meaning that every ball in that urn has equal chance to be selected, right? So now I want to compute what's the probability that the ball is white. So let us denote this event as A, right? A defined as ball is white. How do we compute this? Okay, we're gonna compute this in 2 ways, right? One is from like a straightforward definition and a probability rules. The other is from like more intuitive definition with using some diagram tree, right? Which we discussed in the previous lecture, right? So the first one is because we want to talk about the event, right? We want to look at the event that you select the ball, but eventually you're going to select white ball, right? So this event will have some kind of relationship with the event about which urn you select, right? So let us define B as the event you select urn 1, right? And then what is B complement? What is B complement? Yeah, you select urn 2, right? B complement means that you select urn 2, right? So we want to compute the probability of A, right? So A is actually equals to the union of A with B and B complement. Do we agree? Do you agree with this? Because B union with B complement is just the whole sample space, right? The universal space. Does it make sense? Right? That's a good question. So we can write A as A intersection with B with exactly, right? So, B union with B complement is the whole sample space, right? So which we know is omega. Of course, A is a subset of omega. So A intersection with a bigger set which contains A will be self. Does it make sense? Right? Thanks for correcting the table. This one, this complement of B, BC. This one, or this one. You. Oh, this one. This is definition. It's like B is defined as. It just means. Okay, probably I'm gonna just write it as like B column. It might be easier, right? So, okay. So A equals to A intersection with the whole sample space. Everyone agrees with this, right? Right, because the whole sample space will contain A, right? So your intersection with some bigger thing contain you will still be yourself, right? So now we can leverage the distributive law for the set, right? So this actually equals to A intersection with B union with A intersection with complement of B. So don't ask me why, it's just the rule. We have introduced this in our previous lecture. If you feel like strange, just take a look at our previous lecture. It's just a straightforward application. Okay. So that means if we want to compute the probability A, it is equivalent to compute the probability of A intersection with B and union with A intersection with complement of B. Does it make sense? Right? Because these two things are the same, right? So of course their probability will be the same. Right? So then how do we compute this guy? How do we compute the union of two sets? The intersection, right? So yeah, you're right. So if we take a look at our rules here, see here, right? The probability of union of two sets is the probability of each set or each event subtracted by the probability of intersection of two events, right? We just apply here, right? So of course, in our case, this guy will be viewed as a whole. So we can divide it, we can denote it as A bar. This guy as whole, we can divide it as B bar, right? So if we apply the inclusion exclusion rule, this guy is probability of A bar plus probability of B bar subtracted by the probability of the intersection of these two events, A bar and B bar. Does it make sense? But it's just an application of the aforementioned inclusion exclusion rule, nothing else, right? So A bar is here. So now the question is, what is A bar intersection with B bar? What is it? Yeah, we can write it out, right? So A bar is A intersection with B, right? B bar is A intersection with B complement, right? So now you're gonna intersect them together. What will happen? What's that? It's not A. Why is empty? Yes, exactly. That's the key observation, right? So you see, it's just an intersection of several sets, right? We know the sets intersections are commutative, right? They can change the order, right? It's like a plus, right? It's like plus or multiply, right? You multiply a set of numbers, you can switch their orders, doesn't change, right? You plus a set of numbers, you can switch their orders, right? So if you switch their orders, you see, okay, this is A intersection with A, intersection with B, intersection with B complement, right? So for this guy, we know B intersection with B complement must be empty, right? And yeah, this is your B, right? This is your B complement, right? You intersect them together, it's empty. And then you put an empty set intersect with any set is empty. Does it make sense? Right? So that means this guy, A bar intersection with B bar is simply empty. So the probability of this guy is simply 0. Right? The probability of an empty event is 0. Any question? Okay, if I mean again, if you feel like this is like too abstractive or too complicated, don't worry. It's just several application of the rules, probability rules and set rules we have introduced. You just need to write down by yourself, you will see it, right? So again, we'll recommend you guys to replicate this derivation by yourself, right? So, and then it turns out that this probability is eventually just the probability of A bar plus the probability of B bar, right? The probability A bar, according to the definition, is probability A intersection with B. And this guy, probability of B bar is probability of A intersection with probability of a probability of B complement, right? Does it make sense? Right? So let us look at this event. The probability of A intersection with B. What does it mean? B is defined as a select N1, right? So A defined that you select the ball, right? So probability A intersection with B means that you're gonna select N1, and then from N1 you select a white ball, right? So that means this probability is the probability you select N1, which is half, times given you select N1, you select white ball, right? Which is 3/7, right? Because you select the white ball from the N1. The N1 has 7 balls in total, and you got 3 white balls. So you got a chance 3/7 to select white balls, right? So this is 3/7, right? And then let us look at this guy, right? So A intersection with a B complement. B complement means the event that you select N2. So A intersection with B complements means that you first select N2, then from N2 you select the white ball. What's that probability? Any thought? You first select N2, then from N2 you select a white ball. Half times right? Half means that you got probability 1/2 to select N2, right? And then given N2, you select white ball, this chance will be half again, right? Or 2/4. if you want to write it out, because you got 2 black balls and 2 white balls in total in N2, right? So this is 2 over 4, right? And you add them together. That's your marginal probability of A, meaning that you eventually select a white ball. Any questions so far? Like, this is a good practice, and trying to piece all the definitions together and force to calculate the final number, right? But for this problem, there is a even more intuitive way of doing that, is to draw a tree diagram to show this selection process, right? I guess that one will be sounds a lot easier and more intuitive for everyone. But we hope, I mean, this kind of more abstractive derivation procedure will also help us to review those concepts, right? So the tree diagram will be like, you start the earn selection, right? So you got 2 possible selection results, right? You select earn 1. This will have half probability, right? Remember, we have 2 earns, right? You have equal chance to select each earn. That means you got half chance to select earn 1. You have half chance to select earn 2, right? And then given earn 2, you're gonna select both, right? In earn 1, you got 4 black balls and 3 white balls. That means if you want to select a black ball from earn 1, what's the chance? Yes, right? Given the earn 1, you want to select a black ball, it will be a 4/7, right? And you want to select a white ball, it will be 3/7, right? Okay, similarly, suppose the earn you select is earn 2. And then given earn 2, you select black ball or white ball, what's their chances respectively? Yes, both are, let me just write it as 2/4. Right? That'll be more intuitive, because you got 4 balls in total, and 2 are black and 2 are white, right? They are equal chance to be selected. So you got 2/4 to select black and 2/4 to select white, right? So now our even A is that finally you select a white ball, no matter which path you follow, right? Then the probability would be just calculate the probability along every possible path and add them together, right? Which is just this will be the first pass, you get white ball. The second pass, you get white ball, right? So the probability for each pass is half times 3/7 is the first pass, and the probability of second pass half times 2/4, right? That's exactly the same result as we previously calculated. Any question? Okay, great. Oh, it's taken quite a while to practice these 2 problems. Okay, let's take a break for 5 minutes, and let us continue to give a quick introduction about the concept called independence. Oh, no. A bar is just I use another notation to represent A intersection with B. It's just for convenience. Yeah, there's no, I mean, A bar, you can write it as,
So it's not like.
yeah, E and F, yeah.
And also, one question regarding. So it seems like the multiples at random, so it's like at the same time or it's like.
At the same time. Yeah, if you want to view it as like one by one, then that means like sample without replacement.
And also in that case.
Yeah, yeah,
Order also.
yeah, all of that matters, yeah, yeah.
So if probability is 0, does that indicate that the sample is empty state?
No, yeah, that's a good question. So, yeah, usually we don't go that deep. But there are some kind of non-empty sets whose probability measure is 0. But usually when we talk about this, it's about like continuous infinite sample space. But just to keep in mind, yeah, empty set must have 0 probability.
Oh,
But
so
it's-
it's true
yeah,
other way.
yeah.
Thank you.
There's like a problem where there's like 3 balls in a frame, and are we supposed to worry about like order, like the balls are taken out of that problem? Can I just disregard it and corrupt the like sample space and set notation?
Yeah, you can view it as a sample without
Okay.
replacement.
Okay.
I think some student asked me this.
Yeah.
And I updated the the homework PDF. I just one so you can view the sample without replacement. It's not with replacement.
Okay.
It's without replacement.
Without replacement.
So that means like the orders matter.
Oh, it's the orders do matter.
Yeah.
Oh, okay.
Yeah, like for example, your first sample 2 and then your sample 1 is different from your first sample 1.
Oh, okay, got it.
Yeah. Okay. Hello everyone. Let us continue. Right. So based upon the definition of the conditional probability, then we'll introduce a very important concept. It's called independence. Right. So let's go is like I mean most rigorous and the formal definition, and then explain it in plain language. Right. So we define that even A is independent of even B if the conditional probability of A condition on B is the same as the probability of A without being conditioned on anything. Right, you see that? Right? As we previously discussed, right? Usually they are not the same, right? Take the example, right? I got up late in the morning. This chance is usually not equal to I got up late morning conditional, there's a big snow in the morning, right? But if it is, that means like I'm a really self-disciplined guy, right? I'll get up on time no matter if there's a snow or not, right? So if this happens, right? If this happens, the probability of A is the same as the probability of A conditional even B happens. That means A and B are independent, right? The plain language to explain this is like the probability of A happens has nothing to do with whether B happens. So basically A and B are not related at all. So whether this B happens or not won't have any influence on the chance it happens. Like if it's not that case, like if it's not that case, that means this guy is not equal to P of A, then we say A and B are dependent. Like, but dependent, there could be many, many possible dependencies, right? It could be fairly complicated. And actually, the modeling of the dependency of between random variables or random events is a big topic, is a big branch, right? But for independent, we just need to check whether the conditional probability is the same as marginal probability. So from the original definition, what other results can we get? So this is definition, right? We say the conditional probability of A given B equals probability of A solely, right? Means A and B are independent. But from the definition of the conditional probability, it is the ratio between the joint probability of A and B and the marginal probability of B, right? P of A intersection with B divided P of B. Now, if you multiply P of B on both sides, right? What we can observe is here, the underlying formula. That is the probability of A intersection with B is the probability of A times the probability of B. We say this is another definition of independence. That is the joint probability of A and B, meaning A and B both happens, right? Is just the product of the marginal probability of A happens and the marginal probability of B happens. Then we claim A and B are independent to each other. Any question? So in practice, you can use whatever definition you feel comfortable to check the independence. Right? For a long time, I'm more used to this one. Right? If I want to look at the condition independence in this way, yeah, it will take me a while to think about that. So for this one is easier to memorize. Like the joint probability is the product of the individual marginal probabilities. So this is an equivalent definition of independence. Okay. So now, starting from this guy, okay, as we mentioned, right, this is another definition of independence. That is the joint probability equals to P of A multiplying with P of B. Right? Let's see what others can we get. Right? If we divide both sides by P of A, meaning that I'm going to divide P of A to the left, right? I'm going to be divided by P of A to the left, right? So we say the ratio between PA intersection with B and P of A equals to B, right? Everyone is comfortable with this, right? So just divide P of A on both sides, right? So now, if you look at the right-hand side, what's that? Yeah, it's another conditional probability, right? It's a conditional probability of B given A. Remember the definition of conditional probability, right? The conditional part is the guy who is on the denominator, right? So this is like conditional probability of B given A. And see that we actually get a new relationship. That is the conditional probability of B given A is the same as the marginal probability of B. And remember, when we talk about when we at first introduced the independence, right? What we're saying is that okay, the conditional probability of A should be equal to the conditional probability of A given B, right? So now through the definition, through some kind of like simple arrangement, right? We'll arrive at this conclusion, right? The conditional probability of B condition on A is the same as the marginal probability of B, right? So we get our third definition of independence. You see, this definition is kind of symmetric. So P of B given A equals to P of B is another definition of A and B are independent to each other. Right? So those results tell us independence essentially is a symmetric property. When we say the conditional probability of A given B is the marginal probability of A, right? It is equivalent to saying the conditional probability of B given A equals to the marginal probability of B. Any question? Right. If we interpret it in a plain language, it means that if we know that the chance of A happen has nothing to do with whether B happens. Right. This is the first equation tells us, right? This just tells us the chance of A happens has nothing to do with whether B happens or not, right? Then we could also equivalently claim that the chance of B happens has nothing to do with whether A happens. That's what the second equation tells us. Any question? And mathematically, they're totally equivalent. Like the chance A happens has nothing to do with whether B happens. It is equivalent to the fact that the chance B happens has nothing to do with whether A happens. Okay. So now, going back to the problem we just did before, right? We threw a die twice. And the even A is the sum of the value is 5. Even B is at least one throw is 2, right? We have already calculated the conditional probability of A given B, right? We want to look at whether events A and B are independent to each other. How can I do that? Yes. Right. So we can, following the definition, right? We can calculate the conditional probability of A given B, right? And then we can compute the marginal probability of A. And then we just look at whether these two probabilities are identical, right? If they are identical, that means like A and B are, are independent, right? So let's just do additional calculation, right? So I'm not gonna repeat that enumeration again. I'm just catch my results and read through it. So this is our result, right? P of A given B is 2/11, right? So let me just, let me just write it down, right? So this guy is 2/11. So what's the probability of A? Right? So let's take a look here, right? The size of A is 4, right? We just do this enumeration, right? There are 4 possible outcomes represent the even A, right? And the sample space has 36 outcomes, right? So we know that P of A will be the sample size of A times the size of sample space, which is 4/36, which is 1/9, right? So this guy, oh sorry, this guy is 1/9. So now, does P of A given B equal to P of A? It's not equal, right? Definitely not. Oh, that means A and B are not independent to each other. Okay? They're dependent, actually. Does it make sense? Actually, not necessary. Yeah, you will see some example. Like even you see some kind of overlapping. But if it happens that these two numbers are the same, they are independent to each other. But as to whether logically, whether they're independent to each other, that could be complicated. That'll be some kind of factors canceled in and out. That leads to the results. Any other question? Okay, so second example, just the extension of the problem we just worked out, right? So again, we have 2 urns, right? Urn 1, 4 black box, 3 white balls. Urn 2, 2 black box, 2 white balls, right? And experiment, pick up 1 urn at random, then select ball from that urn randomly, right? So we have calculated the probability of you eventually pick a white ball, right? So which we denote by A. And now we have another event, right? This event is to just talk about the pick urn 1. Want to know whether A and B are independent to each other, right? How can we calculate that? Or how can we verify this? Again, use the definition. So we want to check if the marginal probability of A equals to, the conditional probability of A given B, right? If they're the same, that means whether B happens or not has nothing to do with A, right? So we have already computed P of A, right? So if we can consider, right? This is how we compute P of A, right? So here we have to do a little bit tedious job, right? Just add those numbers together. So, so the first one is 14, 3/14. The second one is 1/4, right? Everyone agrees, right? And then you do some kind of like fraction, then the addition, which would be I think it's 28. 3 times 2, right? That's represent 3/14, right? And this one is 1 times 7, and eventually is 13/28, right? It's just like, you know, high school No, it's high school. It's K8. I don't know. I forgot. Right? K8 math, right? So so we got our marginal probability of A is 13 over 28, right? So let's just jot down, right? 13 over 28, right? Then we need to check what is the conditional probability of A conditional B. So B means that I pick N1, right? So conditional probability of A given B means that, okay, condition on the case that you pick N1, then you select a Y ball. What's that probability? What's that probability? I heard that. 3 over 7, right? Because it is conditional on that you have already picked N1, right? That means your selection of ball can only be picked from N1, meaning that from these 7 balls, right? And the chance will be 3 over 7. And you see, obviously, these two numbers are not equal to each other, right? So A and B are not independent to each other, A and B are dependent. And intuitively, A and B should be dependent, right? Because you select the ball, and you could first select N1, select Y ball, or select N2 and select Y ball, right? It sounds like A and B should be dependent on each other, no matter how you're gonna allocate the balls in N1, N2, right? But let's change the context, change the setting a little bit, right? And then check whether A and B are independent, right? Okay, so now, if we put 8 black balls and 6 white balls into N2, let's see what happens. So now N2 will contain 8 black balls and 6 white balls. Right? Again, I mean, the calculation procedure is the same, right? We need to compute the marginal probability of A and the conditional probability of A given B, right? So the conditional probability of A given B, which means that, okay, under that you select N1, then you select a Y ball, which is 3 over 7, right? That won't change, right? What is changed is the marginal probability. We need to do some kind of calculation, right? So we're not gonna, I mean, use that tedious mathematical formula. We just use this very intuitive tree diagram, right? So now, here the only difference here is here, right? So for the N2, now you have 8. You have 8 black balls and 6 white balls, right? 8 black balls and 6 white balls. That means when you select N2, the chance you select black balls will be 8 over 14, right? And the chance you select white balls will be 6 over 14, right? So now, if we want to compute the probability you select the white ball, which is the even A, right? Again, you need to calculate all of the probability for every pass and add them together. So the first pass is half times 3 over 7. The second pass is half over 6 over 14, right? And when we add them together, you see that it is 3 over 14 plus, and this guy, you cancel 3, is 3 over 14, and eventually is a 3 over 7. Right? Again, you can verify this after that if you don't feel catch up, but it's straightforward, right? So now we have the marginal probability of A is 3 over 7. Right? It is 3 over 7. Now, what can we conclude? Yeah, according to the definition, the conditional probability now is the same as the marginal probability. So now, in this case, A and B are independent. Sounds a little bit weird, right? But this is like by definition. Then we probably could think about why, logically why A and B are independent to each other, right? So one thing you can think about that is that you see the ratio between black balls and white balls in N1, N2 now are the same, right? Like 8 over 6 is the same as 4 over 3, right? So actually there's no difference between you select from N1 and then to the white ball, or you select from N2 and from your white ball. So from a calculation, you won't be able to differentiate these two events. That's why A and B are independent of each other. Any questions so far? Okay, great. So let's stop here today. Right, so next lecture, we'll do one more problem. Then we'll give a broader definition of independence. That's all, yeah.